I'm now going to respond to kind of the general sphere of this conversation with some of my own thoughts about how other aspects of machine learning fit in with ABMs, but also the broader enterprise of data science, and uh, sorry, broader enterprise of modeling. Excuse me. Um, and there was interest expressed in surveys on this front of tools of systems data science. And, I sometimes motivate this with a pre-lecture on a systems data science vision, um, which um, where I talk about moving beyond myth and madness. The epidemiologist Phil Zuckerman once said that theory without data is myth, and data without theory is madness. And I've argued that systems data science, the wholesale merging of the two, not as simple superposition, not as simple juxtaposition, um, nor as simply input output of one into the other, it can rightfully be undertaken, help move us beyond this disconnected, ungrounded theory and uh, data that is just used for training without any understanding of the structure that actually is lies behind proper understanding of it. And as I had mentioned, this is something which is a very contemporary issue in the machine learning world, and the leading exponents of deep learning have come to realize this in part because they've run out of training data, or are really being challenged to advance their models, and finding that it's just not enough to throw more data at it, because often, at this point, they've used almost all publicly available text data. I think virtually all publicly available text data, and then some without permission from authors, a great deal of that too. So, I've talked in this boot camp a great deal about system science, right? And system science more broadly, on understanding and managing behavior of dynamically complex systems. And, I've argued here that these systems exhibit certain characteristics that give rise to properties, things like tipping points and path dependence and lock-in effects, etc., that disproportionate effect of heterogeneity, counterintuitive behavior, and cycles and long delays, pervasive impacts, that motivate the use of system science approaches. These need to understand the whole in a way that's very different from what you would assume by looking at pieces. And I've tried to express the perspective taken in this field commonly that, look, empirical data for many empirically grounded projects is very important, but for other projects which are much more stylized, if you look at the Schelling segregation model or Conway's Game of Life, the Ising model, etc., these are models where fundamentally their thinking tools are very simple, powerful depictions of how just a few things arranged in a certain way can explain or give rise to behavior that is very familiar from the world. Now, we are living in the age of big data and data science, and there is a huge emphasis on on data-driven science that has been elevated over the past decade. And here, the goals are has been gaining insight and via analysis of empirical data with computational methods. And it has, this idea of data-driven insight reflects the focus on empirical evidence, right? And while a huge amount of the in practice focus of this, the overwhelming number of uses you see out there are in predicting, not necessarily in time, but like inferring, or classifying. For example, sometimes it's predicting a bit forward in time. If you look at the thoughts of the intelligentsia in this area, the folks who are really guiding the understanding, there's a recognition of the need to understand driving factors, factors that drive the data generating process, what's giving rise to this data, and yet the focus is often on individual data sets, analyze them in their own terms for the data that they have, and not be thinking all that much about the underlying system that's giving rise to them. I will say that much of this is motivated by, of course, the rise of big data, and particularly longitudinal, temporally and locationally fine-grained, so frequent and often quite localized in space or geography, right? Fine-grained data and data that by the 4 V's of that Google talks about, introduced years back for talk about big data. It's not only high volume, that's the big in big data, but it's high velocity, it's high variety, and in some cases it measures things in ways that are more accurate than would otherwise be available, like through self-reporting. So think, people carrying a smartphone which reports GPS location, or accelerometer data that can depict their physical activity patterns through the day, or with Bluetooth beacons that can pick up aspects of contact that would be prohibitively burdensome for them to report, or where they're just through lack of self-awareness, they may not be paying attention in a way that could allow them to memorialize it, to write it down. Here, I feel a lot of attention in terms of hype and kind of buzzwords has been on this idea that we don't need theory. These are theory-free methods. They'll just tell us what will happen next. They'll let us classify this, and we don't need theory behind it. And the idea behind that is all too often that theory is optional. It's great if you have it, but we don't need it. And sometimes there's a certain over exuberance that it's come in my observation that, we can jettison this theory, we'll just let the data speak for itself. Now, I happen to be profoundly skeptical, and my skepticism is borne out, as I've noted, by the developments in the past 5 years, where so much effort on these methods previously touted as theory-free has been on building in essential mathematical properties you want, hence the invariance and equivariance, etc. And sometimes, using methods that have those properties without fully realizing that's what they're doing, like with convolutional neural networks, with many practitioners not realizing that a fundamental engineering reason they're designed that way is to capture translational invariance, so that, like, the cat is equally well recognized on the upper left corner or the lower right corner or what have you. So that's not silly, in its ability to recognize them. It turns out those are important aspects of theory that in practice are built into some methods that are used by people without recognition that they're in fact building on theory. I have a rather textured view, as you might know. I mean, part of my portfolio is teaching elements of AI in public health, and I do so with a rather articulated sense of where I think it's very dangerous and where I think it's useful. But I do believe these techniques that we're talking about here fit into a broader landscape that overlaps with, coexists with, and in some cases can be used synergistically with techniques from data science, machine learning, etc. And I sometimes draw it out like this, where AI is a term that's evolved enormously over my professional lifetime. I've seen 3 rises and falls of AI in my professional life. Or sorry, in my life. The first in the late 60s. Yes, I was born then, in case anyone's wondering. But I was not a professor yet, in case you're also wondering. Once in the late 80s, I went to school and regularly visited AI Alley during the heyday of Lisp machines, etc., and saw the bust of that. And I also saw the rise and early bust of connectionist methods and neural networks. But then they needed some decades later to be effectively trained how to use them to affect that scale and with important insights. This is a complex landscape. AI contains many different particular subparts. Some parts of only kind of indirect relationship to some of the topics of central interest here, which is more machine learning. But many of these other uses, whether it's natural language processing these days or robotics or automated reasoning, certainly spoken language recognition, make use of machine learning. And machine learning, seeks to develop techniques that learn more effectively with successive data and can draw important insights from that data, whether it's classification or inference or knowledge discovery of hidden patterns in data, etc. Data science, the broad enterprise, includes machine learning and AI as a component, but it also includes many other components which are more concerned with building up the infrastructures and the technical mechanisms to allow our ability to use data at scale, and to carry out the sort of analytics that might be needed with machine learning or with computational modeling at a very large scale on data. And this is the sphere of computer engineering and computer science, which occupies other parts of my brain. But a big component, in my view, of the data science landscape is also their overlap with system science methods. And this is not to scale, and I'm showing that there are some parts of system science and dynamic modeling that lie outside of data science, to be sure. But I personally view many techniques that are empirically rich as fitting in to some broader enterprise of data science. And you could argue certain aspects of domain knowledge are relevance as well. This diagram is not perfect. I would note that it's evolving and it probably could be improved in a number of regards, but it does reflect many of the salient overlaps that I think are important to keep in mind. and it highlights areas where data science, for example, is overlapped with machine learning and where it's not, or where AI is overlapped with machine learning and where it's not. Big data is a big driver for the motivations for data science, for needing better algorithms, for needing software engineering, and the sort of frameworks we build up for with architectures like Hadoop and MapReduce systems in an earlier generation, and with effective data, composable data pipelines, et cetera, for good software engineering. But big data is also, an important tool for enabling machine learning and indeed system science. My own view here is, and unfortunately, this doesn't reflect some of my more recent thinking on it. Contemporary systems data science methods. I don't know why it says review of infectious disease modeling. That's irrelevant here. I will say that within the broader context of systems data science, we make use of a variety of methods, and not all are shown here. Topological data analysis is something that I'm very enthusiastic about, and fits into a broader set of techniques that are manifold-based techniques that take into account the underlying lower dimensional structure of complex underlying systems. So you may remember that model we built yesterday with community transmission, and we saw that with certain parameters it could lead to kind of waves of infection. And I made an utterance there that the structure, that the behavior of that system is amenable, since it has these waves over time, it's amenable to a lower dimensional depiction that could probably be pretty good. Now that's I know highfalutin speech, so let me break that down for some people. What I mean is that came out of a model with many agents interacting over a complex network shaped by income, with different levels of crowding and different levels of connectivity and so on. But the underlying patterns of behavior, probably to characterize that behavior, we don't need we don't need that all the information of the running state of the model. We can boil it down into a closer the state of the model and its evolution over time can be described in a much smaller way, much more parsimonious way, with a lot fewer I'll say parameters, but a lot fewer data points. Because ultimately it doesn't require that behavior doesn't require that level, the description of the complete state of the model to capture those salient patterns in it. It can be boiled down to a much tighter description. And indeed, the fact that we can specify it with an agent-based model that itself is fairly compact, with two state charts, or in that case, there are two or three state charts for that one. But the fact that we could specify that model, with a modicum of mechanism, could build it up together quickly, suggests that it has a nice role in sort of specifying that complex pattern. And indeed, that complex pattern is much simpler than you might think by looking at the nominal number of agents and all possible interactions they could have. So anyway, there's a set of techniques that are variously developed by system science and data science communities that I think fit into the broader rubric of a toolbox where system science and data science are synergistic. They include reconstruction of state space, state space reconstruction using Taken's embedding theorem and delay embedding in particular. Techniques based on calibration for parameter estimation. Those shouldn't be separate things, but calibration-based parameter estimation can be seen as a kind of type of data science method. It's trying to match model behavior, emergent model behavior against observed data. Hidden Markov models involving a evolution of some state of a simple, in this case, Markov chain, a simple underlying system that evolves probabilistically according to some very simple mathematics, and has for each state a certain chance of producing certain observables or a certain probability density of producing observables, or alternatively, a certain distribution of possible outputs. That can be seen within this context. And there's techniques involving approximate Bayesian computation, MCMC, Kalman filtering, and techniques that have been our bread and butter for the past 13 years or so, probably 11 years or 12 years, particle filtering, and more recently, particle MCMC. Convergent cross-mapping is a causal discovery technique for discovering from observational data. This is fighting words to some, I know, but it's borne out theoretically and empirically, recognizing causal connections between that are suggested in empirical data from the world, between certain factors in the world, that are certain variables in the world that are varying over time. I believe that deep learning approaches have a role to play here in several regards, particularly as they build in theory, as they are increasingly doing for mathematics, for these equivariance constraints, sensible theory. No longer are they throw at the wall what you can and see what sticks, but they are instead increasingly informed by mathematical structure and potentially some domain theory. Okay, so I don't have time to go into this in detail. I'm conscious of wanting to get to lunch at 12:30. So I'm going to hold my remarks to a minimum on any one technique while trying to give you the gist of some of the how these things fit together, some of these individual pieces and how they fit together. So when we have a system that's evolving over time, there's a set of possible states it can have. And we call that set of states, if we can envision it, the phase space of a system. So if we have a stock and flow model, and forgive me for those who are not familiar, but at any one time, we have a certain number of susceptibles, a certain number of infectives, and a certain number of temporarily immune individuals, then the state space here is nominally of size 3, because at any one time, 3 numbers are enough to specify the state of this system. Nominal. And in an agent-based model, the state space is vastly larger. It's actually rises the nominal state space, the sort of theoretic state space of possible configurations it could be in, is exponential in the number of objects, or geometric technically, in some cases. So number of, agents. So if each agent could be in 3 possible states, Si and R, if you nominally look at how many states 2 agents could be in, well, the first could be in either the Si or R state, and the second could be the Si or R state. If you have 3 agents, so that's 3 times 3 or 9 possible states the whole system could be in. If you look at 3 agents, you get 3 times 3 times 3 or 27 possibilities. And so with an agent-based model, if we try to think about the set of all possible configurations that could be in, We're not dealing with a smaller number like this, 3 possible configuration, a number here, a number here, and a number here are enough to specify it. We're instead talking about, a vast array for any non-small population. Even if the population is size 10, if each person could be in 2 possible states, then you've got 1,004 different possibilities the whole model could be in. So it rises just profoundly quickly. But the actual point is, like, a system like this, if we look at it and we say, well, we can specify this model at any one time with 3 numbers, S, I, T, I. That's enough to specify the complete state of the model. Just like with an agent-based model, if we could specify the complete state of each agent at any one time, they're in this state for that state chart, this other state for this other state chart, and the same thing for each agent, we could specify the state of that model right now. That state, the set of possibilities of that state, is almost always, almost invariably, vastly larger, needlessly larger, in a way, than what you actually need to describe the evolution of the system. So this model, while it nominally has state space of dimension 3, number of people in the S dimension, number of people in the I dimension, number of people in the temporally immune direction, and you could plot each point in its evolution over time in a 3-dimensional space, SITI. The actual dimension is lower. It's 2. And you could say, well, yeah, it's obvious because S plus I plus TI, this is a model with a fixed population. There's no people dying. There's no people coming in. And therefore, S plus I plus TI is always the same. So if I just know 2 of them, I know the other. Given the total population, I can subtract the sum of these 2 to get that one. And that's true. And that's why it's 2-dimensional. So it's because of the symmetry of the system, or the I should say conservation properties of the system. It conserves the number of people of the system. You don't have people coming in and you don't have people leaving, and therefore that conservation means this is actually of size 2. Now it turns out that this, by graphing out a state space, we can get a lot of insight into the evolution of a system. And the key to this is delay embedding. And I want to, so I'm a little bit surprised why my slides seem to be in a different order here. But I'd like to talk about, so it turns out that we can get insight into the structure of this state space, provably, through what's called Taken's embedding theorem, where we have a given sequence of observations from this system, and for each point in that sequence, we plot it out in a space, where we plot the current value and the value a certain amount of time ago. So it turns out that will give us insight into the structure of the state space. I'm showing here some data. It's actually not constructed with that right now, but it's showing data from during the pandemic, involving daily reported cases and daily reported deaths here, and plotting it out over time. And you'll notice a certain shape of this, a certain loopy shape. So we have cases and then deaths. There's a certain structure that emerges from this. We don't have many that are way in here or many out here. And given a certain value, a point in here, how it evolves has a certain structure geometrically to it. Or more to the point, topologically, it forms a loop that returns this initial state. Same thing with, daily admissions and, for example, beds full within these systems. These two have a certain structure to them that is associated with these underlying loops. And, other ways of plotting out data that were used during the pandemic, for example, used some similar mechanisms. So here are, for example, total confirmed cases versus new confirmed cases. And they found that, over time, systems across many different jurisdictions, whether it's Ontario or in Australia or in Indiana or the South Korea or what have you, the number of total confirmed cases, if plotted against the number of new confirmed cases, tended to follow this certain line and then tended to turn down. So it's a generally sparse graph here, right? Just like this is. This is not all over the map that it just can hop all over. There's a structure to this. Where it is now sort of dictates its future evolution in some structured way. This is structured to this, a structure to this, and a structure here. Here's new cases in past week and change in the cases compared to the previous week. So change in the case rate, excuse me, compared to the previous week. And you'll find, again, a very regular structure here. When we see this emerging in empirical data from real-world systems, it's whispering to us about some underlying structure in the system that's producing it. If it were totally random, we would have a collection of dots here with no rhyme or reason between how they evolve. If each time it was a IID process and independent and identically distributed, we would have, a collection of points maybe exhibiting some covariation between these. But instead, what we see is defined trajectories that evolve, and they evolve in ways that are similar across different jurisdictions. Here, different, regions of the UK, and you see these sort of characteristic patterns. We saw the use of these diagrams grow quite pronounced, particularly in the UK, for understanding evolution of these systems in a data-driven way, in a way that recognized the regularities of the data. And just as we plot out a hurricane over time and its path over time, in these sorts of diagrams, you can use a certain sense of where it's going to give you, and where it's gone in the past, to give you a sense of where it might continue to travel in coming days, much as we can do, for example, with something like this. So these diagrams achieved prominence during the pandemic in some quarters. They were applied some in Canada, applied certainly by our own team. But what I want to highlight is that these patterns come about because of the underlying structures of the dynamical systems involved. This is not an accident that plotting things out in these forms yields regular structure. We haven't just stumbled upon some strange property of this particular data set. What we're seeing here is whispering about an underlying system, and it's related to this notion of a phase space and the structure of the phase space. And these different diagrams are telling us some about the underlying structure of the system that gives rise to them. So what we're talking about between now and lunch is coming together of a set of traditions from data science, including visualization, like we've just seen, but from system science and dynamical systems area that can jointly lead to great insight and jointly be extraordinarily useful. These were our bread and butter during the pandemic. It was through these techniques that we advised, across Canada, future evolution of each jurisdiction, through contacts with PHAC, through contacts with FNIB for First Nations reserves, but also for our own province here. And I'm going to talk about these techniques as ways that data come together with models. And we'll talk a little bit about this relationship as time allows behind the underlying state of the system in its state space and uh, what comes out in diagrams of this sort, which plot out the same variable versus the same variable lagged or two different variables from the system. So, the most basic form of bringing together models with data, almost doesn't need to be highlighted as a data science technique, but it is about grounding the model in data. And this is about informing parameters for a model. You folks have seen lots of models now built in this boot camp. You've built many of them yourself. And you've seen us plug data points into them and me to suggest values. But the fact is that, for an important class of models, empirically grounded models, empirically rich models being a subset of that, we often, for defensibility of the model, for scientific ability to scientifically justify it, for it to withstand scrutiny, for it to secure confidence, we need to put effort in to have informed choices for parameter values. We've talked about how model structure is often a more profound determiner of model dynamics yet than the particulars of parameter values. And parameters select within the behaviors made possible by model structure, what particular sequences, in what particular trajectories or modes of the system we see. So, for example, we saw in that model yesterday of crowding and income-based disparities in infection spread, infection burden, we saw that for the default parameters, the infection, there was just one outbreak, and it would die on. For alternative parameters, we saw, oscillations and not totally periodic, but quasi-periodic. And here, the particular values for the parameters shaped what mode, quasi-periodic or single outbreak, would be exercised, or made one much, much, much more likely for a stochastic model than the other. In general, you're going to be informing, as Wade asked in response to a question from Roselle on the first day. In general, you're going to be seeking to gain sources of estimates where possible for certain data points. And these can come from a variety of sources. They may come from, from surveillance data, from controlled trials, from studies of, duration of infectiousness for hospitalized patients who were in the hospital when they became infectious or presented shortly after infection. In some cases, you may have very controlled studies that have reported randomized clinical trials estimates for certain efficacy values, for example. In other cases, what your model needs is data, for example, about parameter assumptions about your contact tracing system. Maybe it's about how many people are traced per case, how many contacts are traced per case. And you can talk with people who are experts in that system, who are involved in running the contact tracing system, and get an estimate of that parameter. Maybe you want to know something about the average age or about the population demographics. You may use, census data for that. So there's many sources of these sorts of data, but, generally speaking, to make your model defensible, you want to put time in to estimating these parameters where possible. Some of them might come from other models that are peer reviewed and made similar estimates. But sometimes they may come from judgments of system stakeholders who have a lot of experience working with this system and are documented as such. I did want to emphasize, though, something I emphasized in that first day, which is that unlike a spreadsheet model where you plug in data for certain cells and it outputs data for other cells, or like a decision tree where we plug in assumptions about the probability that each path in a chance node will be exercised and it gives us results. Dynamic modeling has a phenomenon that allows much richer opportunities for grounding the model. And that's because we can take advantage of the emergent behavior of the model over time, and we can compare it against comparable empirical data. So we have data from the model, and we judge it against comparable empirical data, and we use that to better refine our model assumptions or a model representation of the state of the system. And this general description will hold true for much of this talk, for many methods. It holds true for calibration at its most basic level, but also for approximate Bayesian computation, Markov chain, Monte Carlo approaches, and in a generalized way that's informing our understanding of the distribution of state in the model right now, our sense of the relative likelihood of being in different states. It informs particle filtering and particle MCMC techniques. So I view these techniques as really providing us avenues for ways of using the broad range of data to which we might have access, but which don't relate to any one parameter. So those models that we've been building, if we were to look at the spread of infection within the context of our neighborhood mobility model, for example, or if we were to look at that, the model we built prior to that, which involved, crowding disparities, for example. In this case, in both cases, we are dealing with phenomena involving like infection spread that produces certain patterns over time that might be compared against, similar data from the world. So in running this model, right, we might see some patterns emerging in terms of associations between income and infection count. Perhaps there's some data from the world, from clinical presentations of individuals. At a more basic level, we might count the number of infections in this model, occurring in this model over time. And we have a certain pattern in the curve that results from that. And perhaps there's similar data in the world to which we can compare model results in terms of cumulative case count or in terms of incident case count, etc. So here we may have data that can't be boiled down to any one parameter. That curve that we just saw, for example, is not purely a function of how long it takes someone remains infective. It is affected by that. If this were essentially instantaneous, it wouldn't be spreading at all, and the infection burden across all incomes would be zero. It is affected by contact, and therefore by contact rate, but it's not just reducible to that. It's a lot more than that. It's contact, yes, interacting with how long people are infected for. It is affected by waning of immunity, but it's not only affected by that, the count of people infected over time. So when we have data sources for the world, on empirical data, we can compare with model outcomes. We generally will be able to use it to constrain our plausible assignment of values to parameters, and particularly for parameters where we don't have good data, we seek to match the model, shown here in kind of this curve in gray and this curve in red, against the data. And we do so for many data sources simultaneously. So if we have data from the world on different outcomes, we seek a model that stays true at some level, that reproduces them for the historic period before we look to counterfactuals as closely as possible. And generally, this will be a very different set of data, and sometimes significantly more data than we have on any one parameter. Getting those estimates for parameters may be hard. We'll do our part, but there may be, and almost inevitably in a sufficiently rich model, there are parameters we don't know the values. But this provides us a different avenue of working to arrive at estimates for those parameters, because we have different sources of data that we need the emergent patterns coming from the model to match. And we can tune values of parameters that we know less to best match that emergent data. So here, we're tuning values of less well-known parameters to best match these observed data. We're adjusting our assumptions in the model on things where we don't have good grounded information or where it's highly variable to match different empirical data points, or in this case, time series. And there's a learning process. Sometimes we learn from this that our model structure just can't effectively match these. And that's an outstanding opportunity to learn with the model and sharpen our understanding. This is part of model learning, is figuring out, does it add up? Can it produce behavior consistent with what we see from the world? If not, it's a good call to action to modify some assumptions in the model. Calibration is a topic you'll find dozens of videos of me talking about. It's a topic where Wade has tremendous experience in the trenches. But fundamentally, it's about tuning parameter values of less well-known parameters so that model emergent behavior best matches sets of data. And to do so, we have to specify a set of different information. We have to specify what things we're trying to match, and an objective function that specifies how much we care about each attempted match. So we have what's called an error function or a discrepancy function or some measure of how good a model matches to the data we're trying to match. So we have data we're trying to match, we have model output, how good are they? And we are seeking here to have that match be as close as possible. Beyond that, we need to specify what parameters to vary and over what range to vary them. And any characteristics of the desired tuning algorithm or optimization algorithm. So here it's useful to think about not state space, put that aside for a minute. That underlies model behavior, but parameter space. So if we have a certain value for one parameter, so here are three parameters, mu, beta, and tau. And if we have a certain value for mu, that will determine this, our value on this axis, certain value for beta that will determine how far we are back here, a certain value for tau, how far we are up. So when we run the model, we're trying to explore this space, and when we calibrate it, to try to find the point in this space, the value, a specific value of mu, beta, and tau, where the model best matches the observed data. Okay. Now, these strategies are bread and butter in a lot of modeling projects. AnyLogic provides good support with its calibration mechanisms for these. But it does have some significant limitations. I've listed some here. The single value you get out really doesn't communicate uncertainty about that or the breadth of other areas where your matches is just about as good. You're positing this particular model and not a set of possible models, and you're estimating only parameters. You're not questioning your understanding, say, of the state of the system at the current time. So these other techniques that we're going to be talking about provide more sophisticated ways of taking on some of these challenges. Calibration is similar in spirit to approximate Bayesian computation and MCMC type approaches, but they have a more general way to express how well the model for different parameter values matches the empirical data. And they can provide you not just one data point where it matches the best in parameter space, but a distribution of plausible values for that parameter. That's called the posterior distribution for MCMC, which expresses, given the data you have and given model structure, what is the implied probability distribution for the value of the parameters that you're trying to estimate. Approximate Bayesian computation is a technique that is notable for being supported in agent-based models. I've in fact provided you as part of the example library in ABC, or this is sometimes called ABC, an ABC model which basically allows you to match empirical data and get out a distribution. It's not strictly a Bayesian technique. It's a technique that is based in probability theory, which is applied by statisticians sometimes, but it's a very simplistic technique and very straightforward to actually implement. It does give you a distribution. It doesn't require you to posit, to put all your eggs in the basket of one parameter, one value for each of the parameters. Rather, it gives you a mechanism for having a distribution over parameter values that's informed by the models. Even if it's not strictly a Bayesian technique, it's a pseudo posterior, not a true posterior. You specify a cost function, a discrepancy function. That's something that says, if I have a parameter value and I have some empirical data Y, how good is the resulting behavior that comes from that? How good is that compared to the the resulting data. You do have to specify that in some particular model. And then you can arrive at, this is the pseudo posterior, which is arrived at by sampling possible values for these parameters. So this has some virtues to it. It's very easy to implement. I've given you an example model for it. It's readily done for agent-based modeling. It's not terribly expensive. And it's something that's computationally tractable, is what I mean by that. And in principle, you could use it to sample from different models. In fact, here you're selecting different models, but it gets more complex because if those models have different parameter spaces, then shifting between them gets to be quite a sophisticated matter. There are some disadvantages. It's not grounded by the rigorous Bayesian mathematics of MCMC or particle filtering or particle MCMC as commonly employed. It can be hard to identify discrepancy functions, but that's true for calibration as well. And importantly, for some of the other methods we'll be seeing, it, like calibration, does not admit a possibility, even for a stochastic model like an ABM, that it doesn't help you estimate what's going on at the current time in terms of the model state. It doesn't help inform your understanding of the current situation in the model based on the observed data. Now, in a way, this provides an approximation for a sort of runner-up to a simpler runner-up to Markov chain Monte Carlo approaches. And here, what we're doing, these are in a broader space related to these other techniques, but here what we're doing is we're trying to estimate in a rigorous Bayesian way sample a distribution for parameters in light of observed data over time, or observed data points at a particular time, typically more than one. And you have some prior distribution over parameters, some plausible and subjective, some plausible values. It might be as simple as a uniform distribution. You're not sure where it is in a certain range, but it could be a sort of truncated normal or what have you. And then you use MCMC to arrive at a formal Bayesian posterior, a formal estimate of the probability distribution over parameters that will highlight for you not just one parameter that seems to lead the model to best match the data, but other plausible ones will have high probability density, high chance of occurring, high likelihood, you might say, of occurring. I'm not going to go into this in detail, but it involves running the model, as you might expect, again and again, and changing the values of the parameters you're guessing again and again, like calibration, but doing so in a way that's much more grounded by rigorous Bayesian theory. So you're exploring possible areas of the parameter space, trying to find cases where that the model makes so for that assumption of parameters where it makes the model produces behavior similar to what we see from the world. And for those that are quite good matchers, we'll stay there for a while. So we'll have many samples from that. Here, this is a sampling technique. So it's emitting samples. So when I say it's estimating a distribution, it's because it gives us many particular possible values for the parameters. It'll just keep on outputting different possible ones, and some will concentrate on certain areas of space. And those ones indicate that that's an area of space that's quite likely. maybe certain ones will be very rare in what it's outputting. There, it's less likely the model explains this. So the posterior distribution here is produced by sampling. You have a candidate value, and this is arrived at randomly randomly changing the value you used in the last iteration, and you see, should I accept it or not? And there's a rule for this that you can compute, and you either accept it, meaning you output it, or you reject it, and then you output again where you're at in the space. And so here you're kind of going, if we imagine this as a one-dimensional space, this is kind of different possible parameter values. Just imagine that right now we have one parameter value. And maybe you're here currently, and you're running the model, and you find that you have a candidate value, so you perturb theta to get a theta star. And you find that, okay, it's the posterior at that point as calculated from the likelihood function and multiplied by the prior distribution. It's actually higher than my current point. Well, then I will be moving there with a high likelihood. In fact, it will be likelihood of 1. By contrast, if I sample and I find one where it's less probable than here, I'll move there only with a lower probability. So I may well not move there. And this means it tends to stay in areas of the space which are more probable and keep on emitting those, keep on outputting those parameters. So this is a way of arriving at an approximation to a posterior distribution, where we have lots of samples from these areas again and again and again, and from areas that are very unlikely, we'll have only a few samples. And by plotting out in this case, a histogram for that, we would see a curve like this. It would show, given this model, which parameter values are more plausible and which are less plausible. And notably, it supports, unlike maximum likelihood estimation, for example, multimodal distribution. So maybe there's multiple values of parameters that are plausible, that are very plausible, but they're not in some sort of clustered way. Now, I've shown you here with a single parameter what this looks like, but in general, in one of MCMC's great strengths, and strengths of PMCMC, as we'll see, is that it can handle many parameters at once. So 5, 10, it can handle. And jointly, so have a joint distribution between them. So it might say, well, parameter A can be high or could be low. But if A is high, B has to be low. Or if A is low, B has to be high. So it captures this sort of this joint variation in them in this parameter space. I want to highlight an old technique dating from 1960s, which I can assure you is in your smartphone, Apple smartphone, so with iOS or Android. The map software will be running the Gllmpse filter. Every flight you've taken, chances are it's using the Gllmpse filter in its avionics software to calculate your position, and to update your position based on some model of the plane and its thrust and its aerodynamics on the one hand, based on theory of how it will evolve, should evolve given that, but also based on your altitude, but also based on GPS measurements, for example, coming in from satellites. And each of those has error associated with this, and this is a way of putting them together to get a maximum likelihood estimate for simple systems of where you might be next. And this is particularly well adapted when you're getting measurements very, very quickly, maybe every second or every few seconds. It's very computationally parsimonious, and it's quite specialized as well. Quite specialized to certain types of systems. So the idea here is, look, we're trying to estimate the underlying state of the system, like where we are in a plane, or in a model that's evolving stochastically, what its current state is, from based on data coming in. Thank you. Wade points out that Rudolf Kallman passed away in 1916. I'm sorry, 2016, not 1916, 2016. So the Kalman filter here involves balancing two, taking into account, look, the system behavior is uncertain. When we have a stochastic model, we have a model that's evolving stochastically, we don't know exactly what it's going to do next. We have a range of possibilities of what it's going to do next. But over time, the real world is doing a particular thing. It's not doing a set of possibilities. It's undertaking a very particular trajectory. And we would like to keep our model grounded in what it's actually done so that when we look forward, we can take into account like the current situation. Otherwise, our estimate of the current situation is ungrounded by observations from the world. And we're going to be very broad in our thinking, very, unnecessarily uncertain about what's going to be going on going forward, because we're not taking into account what has been going on. And do I have a nice? No, I don't have a nice picture of this, but I think of it as a little bit like weather forecasting. What you do with common sense with weather forecasting. So all of you probably looked at the weather, sometime in early August. And that weather report might have estimated the weather for today. But you would never want to rely in deciding whether to go outside today, whether to carry an umbrella or not, to rely on that weather report from the beginning of August. I mean, that would be madness, right? I mean, that weather report may have been based on the world's best weather model, but you actually know what's happened since then, right? You know what was the weather last week. You know what was the weather yesterday. You know what was the weather the last few days. And that can sharpen hugely the estimate for the weather now. And over time here, we're getting data in about what's actually happened. There was some uncertainty. We didn't know which way the thunderstorm would move, or that heat wave would reach up to your area. There was uncertainty about the interaction of several fronts. But if you take into account what's been observed in recent weeks and days, you can do a lot better of an estimate of whether it's raining right now and whether it's likely to rain between now and sundown. It would be a fit of madness to rely on weather estimates from 3 weeks ago. That was a very good model that they were based on, maybe the world's best model, but there were a lot of uncertainties associated with that have now been resolved. That heat wave never reached your area. There was high precipitation in the neighboring city, but not in yours, etc. So here we have an underlying situation which is evolving in an uncertain way, and we want to, instead of just throwing up our hands and saying, well, we don't know what the situation is going to be tomorrow, except, relying on this model, we want to take into account the observation. Wanted to take into account the ongoing observations, not just the model, but the observations. So here we are balancing some trust in our model, some understanding of theory for how the natural history of infection evolves, for example, for COVID, how transmission tends to occur, how long the latent periods are, the level of infectivity at different points of the course of infection. We're seeking to balance that theory as captured by our model with measurements coming in. It's a matter, in my mind, of being humble. It's a matter of being a model with humility. We trust our model is thoughtful and considered and informed. But like that weather model, we don't trust it to predict the future because there's a lot of uncertainties in the world. And we want to keep that model informed by empirical data that have come in over time, that have told us, was there an outbreak last week? That have reports on whether a new variant has arrived or what have you. So the Kalman filter is a very simple, I would say simplistic technique, but it's suitable for certain types of particularly linear systems where you want to balance the model and measurements. And you do so in a way that gives more credence to measurements that are more accurate. And if the model has been grounded recently by an estimate, you give that more credence, in terms of weighing it. If the model it exhibits less variability in its projection, the evolution has less uncertainty, you trust that more. And so you weigh what weighs this, what determines which way it goes is your sense of the uncertainty or the degree of uncertainty in each of these areas. And there's a formal sense to this where you balance the essential the variance as measured through covariance and variance matrices, etc. The challenge for a lot of Kalman filtering techniques is they're outstanding for mostly linear systems for very short periods of time, or systems that are nonlinear for very short periods of time. But if you have a nonlinear system, like we have in spades in health, which has tipping points and which has multiple potential equilibriums, where path dependence, etc., you're in general going to have multiple basins of attraction. It could be in one area or another area of the system. In Kalman filtering, even the linearized extended Kalman filter for nonlinear systems, it is doing a local analysis based around its current understanding of where you are. And this system and this analysis can get stuck where it thinks you're up here and you're really down here, and it's bullheaded. It interprets all the data and updates the model, assuming that you're up here, and it may be self-confirming, whereas really you need to be down here, and it's not open to that possibility. So to address that in a way that is much more robust vastly more robust for nonlinear systems, vastly more robust given the sort of rates of data we see in certain other systems, generations of researchers over the past 25 or so years have turned to other approaches, and particle filtering or sequential Monte Carlo or SMC techniques are one of the bread and butter techniques here. They saw particularly huge techniques early in robotics, so that a robot could estimate, given sensor data, where it is in a complex environment, recognizing that the model of the robot's movement has some uncertainty associated with it. Maybe it's on a more slippery floor in some cases, or gets traction in other cases, or what have you. But there's uncertainty associated with its measurements from the observed environment because of low light levels or whatever. But particle filtering has been part of the bread and butter of engineering and scientific methods for years, because it's much more robust when you have a nonlinear model to what state you're in, and it's much better able to grapple with uncertainty and give you a sense of the distribution of possibilities within the broad system. So here, we've been applying it in epidemiology and public health now since about 2014 or so. Maybe it went back to 2013. But the idea, at a moral level is kind of similar to the humble modeling idea behind the Kalman filtering, where we have a model that is mechanistic, that anticipates how things will change in the next little bit, but it's stochastic. So it has some uncertainties associated with it. An agent-based model is one example for this. And then we have some data coming in over time. And we wish to ground that model's estimate of the current situation with this data to best anticipate what the current situation is and where it might evolve. So this was, as I said, one of the bread and butter techniques we applied through for all provinces in Canada, for reports circulated to them regularly through Public Health Agency of Canada, and for First Nations reserves through reports circulated to them through the Indigenous Services Canada, Health Canada, and there we could make use of data over time about COVID, from cases, persons tested, deaths, ICU information, hospitalization, admission, census, wastewater data, and we could use it to estimate our understanding of really what the current health status of the population is, in a way that was very savvy to the fact that, for example, there may be unreported outbreaks for a certain number of days. There's uncertainty, reporting is incomplete, and there were underdiagnosed cases. There were oligosymptomatic, mostly asymptomatic individuals spreading infection. And we could estimate that system and estimate the current situation, including basic reproductive number, effective reproductive number, estimates associated with the number of undiagnosed cases out there, et cetera, and project it forward. So here, you may recall with MCMC, we were sampling from parameter values and trying to get, through sampling, kind of a distributional understanding of what plausible values of parameters are. Here, we're not predominantly focused on parameters. We're predominantly focused on the underlying state of the system. Is it raining today or not? We're not trying to do this to estimate parameter values predominantly. We're trying to do it to know how many undiagnosed infectives are there out there. How fast is the infection spreading? How many how many cases of asymptomatic individuals might there be? Here we want to know, what the situation is right now in terms of the latent state of this system. And we want a distribution over that latent state, and that's what X is here, in light of the observed data. So rather different from MCMC, where we're trying to estimate parameters, here we are taking as a given static parameters. We may estimate some, like with Kalman filtering, some dynamic parameters that are varying, but really our focus is in estimating the state of the system, because we don't want to be operating off an understanding of the state of the system as we had it projected forward from months ago. Just as if we don't want to rely on an estimate for whether it's raining right now outside based on an estimate from the world's best weather model from 3 weeks ago. That would be a fool's errand. We want to use updated understanding. And this is what particle filter gives you. It gives you a whole distribution over the latent state, a whole joint distribution over the latent state, given observed data. And there's going to be large amounts of that latent state which are not observed, but which can be inferred given the data that's available. And what's really important from a systems science perspective, or a systems data science perspective, is to recognize that all these things here, the wastewater data, the cases, the persons tested, the number of deaths, ICU admissions, and number of people overnight in the hospital, et cetera, these are all whispers of a common underlying system. And by estimating the system, the state of that system, in a distribution, we can understand why all these different data sources are exhibiting the patterns that they are. And we can use data about these things to inform that estimate of the underlying system. So that's what we're doing here. We're informing our estimate of the current underlying system here, and using that to reveal things that we otherwise don't observe, like the number of undiagnosed cases, or how fast the infection is spreading right now, and to project forward and to ask about effects of interventions given the current situation. So I'm not going to have a chance to go into this in detail. I don't think that would make sense given the distribution of our time. Just suffice it to say that each particle here is a competing hypothesis about the current situation in the system. So here we have a set of particles, and they jostle to best predict the system. Each particle thinks there's a current situation now. One particle might think there's lots of undiagnosed cases. There's just you wait and see. There's going to be a lot of reports of them soon. There's fewer people, in an asymptomatic state, and the infection is spreading quite quickly. And then there's going to be other particles who say, no, you're out to lunch. There's actually only a few undiagnosed cases. The burden I agree with you that the burden of asymptomatic transmission is quite low, and the infection is spreading quite slowly. So each particle is a complete hypothesis about the state of the system. We have done this with agent-based modeling, with some mixed effects. There's some work in the literature suggests it can be successful, and we're due for another round of this. But it's a very natural point. And the idea is that these different particles compete to explain the data. And there's a survival of the fittest. Particles that are more consistent with the observed data, that produce results from the model that are closer to the observed data, will tend to thrive. Those that are inconsistent with the observed data, time after time, will be downweighted and will tend to disappear. They will tend to be outcompeted and others will take their place. And this is based on a theory called importance sampling. So it's a very powerful technique. It does not require any parametric specification of the distribution. No, in general, we're just sampling from it. There's no assumption that it needs to be, a normal distribution or anything like that. It's just we're just sampling from it. And our own work, we've applied it now to 1 to 2 dozen different cases from wide variety of conditions. It was our bread and butter of daily estimates during the pandemic. And compared to calibration will give you some estimate for parameters that will allow you to best match some data. Particle filtering grounds your understanding of the model based on that data. It updates your understanding of the current situation of the model. And it allows you to anticipate what's going to go on. This is real world data from outbreaks with measles in the pre-vaccination era. It allows you to estimate what will go on the next little bit in an extraordinarily accurate way. We've done similar estimates with pertussis, for example, with TB, et cetera. And by estimating the current state of the system based on what actually occurred in terms of size of outbreaks and so on in the past leading up to now, it's just like taking the best weather model in the world, relying on a situation of that calibrated version of the model as it predicted things out here from 3 weeks ago, versus having every day it regrounded in its understanding of the situation based on new observations, maybe every 3 hours. You're going to get vastly better understanding of what's likely to play out between now and tonight from a weather model that's regrounded every 3 hours than that same weather model with all the same calibrated parameters and so on from 3 weeks ago. It's just going to be night and day. And so it is with epidemiological data. So it is with real world data. We could take this data, combine it with our dynamic model in a turn the crank sort of way, and use it to reground it. That then makes that underlying estimate of the current situation vastly, vastly better. And that provides us with the far better ability or grounded ability to anticipate the effects of interest. So there's a question, how granular and accurate do we need data for us to be? It's super robust for that. It's it is very tolerant of this, and it can be very high level. During the pandemic, we were dealing with all very, very high level data, very high level data. And the point is, and this is the system science understanding, like these data points that are in each of these data sources are not independent of each other. And they are all reflections of an underlying system. And we can have data at an aggregate level on each of them, and it will give us pointers to the underlying state of the system that triangulate between everyone. It just says, for this to add up, this must be the state of the system. Regarding confidentiality, it's not going to finger. So generally speaking, even if you apply this with an ABM, it's not going to say Mary's infected. You got to go find typhoid Mary, or, John, you got to bring John in for testing. This is going to give you a sense of the underlying burden. And it's going to say, well, look, there quite possibly is an incipient outbreak here. You got to really watch maybe this area. Or, okay, this area is very unlikely to have an outbreak any soon because it just had an outbreak 2 weeks ago. And because you're bringing together theory in the model to explain this data, and because you're grounding estimates from the world in light of that theory, it's asking, how can my theory of the world best jibe with this observed data? It must mean this. And that allows you to sort of have these estimates that are very grounded about what's going on, that take all these different estimates, put them together into a single consistent picture in the model. That's what's going on. You have like one model that explains all these different data sources. And so when they depict something, you say, oh, okay, what they're telling me collectively admits one consistent or a small number of consistent interpretations. Or if it's ambiguous, you narrow it down to those possible ambiguous interpretations, and you watch them carefully for how they will be resolved through further data. So generally speaking, I can chat later about it, but there's minimal concerns about confidentiality. It's not going to give you anything at an individual level, certainly. But aggregate level data is, an outstanding match for these techniques, which may lessen confidentiality concerns about releasing data compared to, something that is very, very place specific or person specific. I'm, by the way, I'm familiar at a broad level from collaborators about some of the issues with confidentiality when it comes to certain types of operations that might be associated with animal health and like the food supply chain and so on. I hear you. So look, even a fairly articulated underlying model paired with particle filtering incoming data, it can just ground your estimates from that model. In this case, we're dealing with we're trying to match up for children and for adults the number of measurements. And you could see it's not perfect, but it's pretty good in matching up the empirical data that are occurring over time for just annual data. This is annual data that are being reported, and you are able to ground the model on an ongoing basis to be much more accurate. Here's something further. So having grounded it, you can then project forward vastly, incomparably better. You're not dealing with, a situation where you calibrated a while ago and you're counting on that model to tell you what's likely to happen. You're regrounding it in an interpretation that's understood in light of the theory. And then you're projecting forward with that regrounded model what will happen. And this is just like using a weather model that's been updated in the past 3 hours and every 3 hours before that to estimate what's likely to go on tonight. You're going to have a very good understanding if there's a high risk of thunderstorms or a high risk of precipitation or of high winds. It'll, looking forward, this is data in which it's trained here. And you've gotten to this point just at the start of an outbreak, but it doesn't know that. This is all in the future. It's not trained on any of that. It's not informed by any of that. It's just informed by this. Think of this as like the weather reports over the past, every 3 hours for many days. And then you're asking, okay, if you're here, you know that there's been low outbreaks here in recent months. And similarly, down here. What do you think is going to happen soon based on this? It's exceptionally good at predicting outbreaks. It will just say, well, look, there's been very few cases recently. This was a small outbreak. It knows the susceptibles are building up because it is a theory-based model that's building this up. And it knows the only way to make sense of this data is, okay, there's probably more and more susceptibles building up. And so I'm at high risk of a coming outbreak. It doesn't know for sure what exact day it's going to start, but it knows you're due for some rainfall very likely in the next 12 hours. I don't know exactly what minute it will start. I don't know the exact hour, but there's a high density. This is a distribution, right? A high probability that you're going to get some outbreak, and it could be as high as up here. So this is how this works. Same thing. So here we're in the middle of, from the peak of an outbreak. We've observed this. We've seen more and more cases. we're asking, what do you think it's going to do over the next little bit? It says, oh, look, it's going to be going down. It's going to be going down. We've had so many cases already. We've had so many occurrences, and we know, that will largely drain the number of susceptibles that have built up from over this period. It's a theory-based model, and susceptibles are very few. So we're gonna it's high cases in the past few days, don't get me wrong, or past few months here. It's high number of cases in the past few months, but it's the nature of things. It's the nature of how measles works, that it has to go down. Like it's got to be going down because it's inevitable. We've drained the number of susceptibles. It doesn't add up otherwise. It doesn't make sense. And indeed, predicts a high likelihood and just nails it. And this is not unusual for pertussis as well. We have the same phenomenon. Now, particle filtering, this is why we were using it in the pandemic, right? We want to know, given what we've observed till now, how likely is an outbreak in the next little bit? Or, how quickly is it really spreading, given that we have imperfect reporting of cases? There's many people who may not be going to get tested, etc. And, it can do a good job of this. And that can help us plan interventions. I don't have this shown, but if you think about it, these situations will be very different for the impact of an outbreak response immunization. And if you grounded it and didn't use it to predict, but to say, I want to have an outbreak response immunization campaign, or I want to undertake a big screening campaign, or I want to put in place enhanced contact tracing, the effects of it will be very different here than in one of these cases. And so the fact that you can reground lets you much better quantify like how much gain you'll have for this intervention versus this one. If you're just relying on an outdated estimate, it'll be saying like, how much gain would you have by going out with an umbrella? Well, I don't trust that. It's the best weather model in the world, but I don't trust its estimate from 3 weeks ago to tell me how much I'll save myself grief by going out with an open umbrella or what have you. But if it's trained in the past 3 hours or every hour, like I trust it a lot. It's telling me it's raining, I'm going to go out with an umbrella. It's going to save me a lot of grief. So my point is that by grounding it in what's actually happening, by goodness, in a theory-based way, taking all this data and saying, go figure, like make sense of that in terms of the theory. An understanding, a hypothesis about the current situation makes sense of all of this, and you have these competing hypotheses, it's going to be much better at estimating interventions. Now, there's always going to be some naysayer particles, probably contrarian particles. Just you wait and see. I think there's a hidden outbreak that could be coming. I think there's a lot of undetected cases. Yeah, just you wait. And give those credence. Those are part of your distribution of particles. You might have 100,000 particles, and some that say, I think secretly there's a lot of undiagnosed infectives out there, and you're not reaching them, and they're not coming in for the hospital because they're not seriously infected, but they're going to infect people. And you say, okay, I'm listening to all sides, but the ones that are vastly more likely in my mind are the ones that will, predict an outbreak here. But here, but sometimes you see data for the next few data points that actually makes you wonder, oh, maybe those folks are onto something. Those particles that I've been saying, I'll tolerate you, just, keep on challenging my assumptions. Those data points, if you start to see outbreaks, you'll start to invest in those. Say, oh, okay, I'm going to give you more of a hearing. I'm going to upweight my confidence in you. And then you'll get to the point where those are the dominant ones and they multiply. The survival of the fittest, the ones that were had a optimistic view die out, and those ones or many fewer, and those ones that have been the contrarian ones will multiply. So it's awesome for taking into account outbreaks, for example. Okay, that's why, as you can see. one thing I'm not showing you is um, the ability to predict outbreaks. For those familiar with machine learning measures, we have an AUC, an area under the curve, of over 91% for predicting outbreaks in the next month using using pertussis. I think it's 90 point something for measles. Okay. Um, PMCMC. So time is short. We're coming up on lunchtime. PMCMC gives you the best of both worlds. It gives you particle filter's ability to reground a model situation so the model depicts in its distribution and possibilities what has happened, but also to estimate your parameter values, to jointly estimate that. And Wade is probably in our lab right now, the foremost expert in PMCMC, uses it with wastewater data and with multiple types of pathogen. Very computationally expensive, but it jointly estimates the parameters, that's the theta, with the latent state of the system. So it'll let you estimate parameters and what's currently going on now. It'll let you get better in your estimate of the parameters. Okay, we don't have time for this. Right. Big data is increasingly around us, but a lot of that data is lower, has data is of different pedigrees, and some data informs you, like data on searches for rash or searches for handling a tick infection or searches on Lyme disease from somebody, symptoms of Lyme disease. You might take that as telling you something about how many people might be being exposed to ticks out there, experiencing potentially Lyme-related rashes. But, it's going to inform you a lot less than clinical data. But these techniques we've been talking about let you have broader distributions of your likelihood, less weight associated with that for taking into account. And one of our findings from this is that if you pair very reliable data, say clinical reports, with quite sketchy data, like data from social media or search volumes, you do much better than with clinical reports. You can actually do much better because it further pins down things. It brings more information to the table. The pedigree is less, and you take that into account, but the weight of the evidence starts to become overwhelming. And this is, in a broad level, similar to some of the transitions that biology underwent in the late 90s, early 2000s, when very super carefully conducted experiments like my wife was doing when she was in grad school were supplemented by kind of uncertain empirical data gathered with novel approaches. And there's a bit of a fight between, this is low quality data. How is it possibly going to inform us? We don't want to pollute our good quality data with this low quality data. But at some point, it became very clear that the data science techniques won out, and the extra information brought in by these lower quality data sources, combined with the high quality ones, if properly combined, they give you much better estimates of what's going on. It's not like you pollute the data by including this, the quality of the data by including this lower quality one. You do so in a savvy way, in a way that takes into account both voices. And so, we had very noisy data. This was back in H1N1 days, on, searches related to H1N1. These days, it's social media data with respect to COVID-19 cases, etc. Right. I think I'll go light on this, although there's some important findings. Time is running out here. I'll say When we have an underlying system, an underlying dynamic system, systems in the world, systems in our dynamic models, how that system evolves depends on the current state, right? How many people get infected in the next little bit depends on how many people are susceptible and how many people are infected, right? The evolution of the system depends on its current state, right? Now, here's the thing. By extension, how susceptibles evolve is not independent of how infectives evolve. After all, people get infected, they go from susceptible to infected, right? Similarly, if we looked at the number of new infections, that's not a solitude from, it's not totally independent of the number of susceptibles. No, there's a relationship. If we look at the number of deaths, it's not a solitude for that earlier model, like for heart disease. It's not a solitude from the prevalence of heart disease. The two are really related. And that's not independent of the occurrence of uptake of smoking. These things are related. The underlying system relates these. Much of this week has been spent building models that link together processes about different sorts of involving different areas of a system, involving someone's smoking status, involving someone's status with respect to heart disease, involving their mortality. These things are not worlds apart. They're not in different continents, independent of each other. They're closely coupled. And data from the world about any one speaks to you about the others. Its influence, it contains information about the others. The fact that evolution of one variable is entangled with another means that the information you gather about number of new cases tells you something about the number of susceptibles. Number of occurrences of heart disease mortality tells you some information about the rate of smoking. Tells you some information about the rate of heart disease. It doesn't totally pin it down, but it tells you something. And back in the 70s or 80s, mathematician Forrest Takens demonstrated that, look, if you have a coupled nonlinear system, you can actually reconstruct the state space of the system using data from only one measurement, because you can reconstruct the things driving it. There's enough data there and measurements over time about one thing, it'll tell you about the others. Okay. And the procedure that was used for this was called delayed embedding. And I referred to it earlier, but it basically involves taking one data point and looking at data points successively further in time ago. Data point now, data point as it was a day ago, 2 days ago, 3 days ago. And this is called the embedding space. So basically for each data point, you get maybe 3 data points. The value today, the value yesterday, the value 2 days before. And you can put that into a space, okay? You can plot it out in a space. And you may say, well, that's kind of weird. Why would you do that? Because it mirrors the state space of the system, provably. It actually captures the same structures as are in the states, the system, the state space of the system. So you're reconstructing the underlying state space by which it evolves. And it turns out reconstructing this way has many virtues. And this is why those graphs we saw at the beginning of this talk, that's the theory behind those graphs, plotting out elements of the state space. Some of them plotted one variable versus another, but others was like new cases compared to earlier cases or what have you. Current total cases and new cases. And you can use this for many purposes. And what it's telling to us in systems data science is that, data about one thing whispers to us about the whole system that is driving that. And if we take that into account, we can get great insights from that data and use it to infer things about the system we otherwise wouldn't have used. And what convergent cross-mapping is about is about arriving at an understanding of what's driving what. To what degree is this associational? So, for example, unemployment and occurrence of suicide occurrences, tragically. To what degree is that just they both tend to be high in certain cases and they tend to be low in others. There's no direct linkage. Or to what degree is there a honest to God linkage between them? Or, suicides among celebrities and God forbid among younger individuals. To what degree is that a causal connection? Or to what degree is there some other third factor that are driving both? These are the sort of things we can probe with these methods through this state space reconstruction. I'm not going to comment on these. I think what we're going to do now is it's 29 past. I think we should break for lunch. I'll offer some additional comments along these lines after lunch. And then we can talk a little bit about how to use the balance of the next hour or two of the afternoon before we have some case studies. Okay, so that's all for now. I will see you after lunch. Thanks. Let's come back in an hour. And I'm going to have to close this so that we can start the recording of the videos. Thanks a ton. See you then.